Right now, 80 light years from Earth. A planet 7 times wider than its own star is racing around a stellar corpse in just 34 hours. That orbit should have killed it billions of years ago. The star it circles used to be a bloated red giant, large enough to swallow anything sitting where this gas giant sits today. By every model astronomers trusted, this world should be gone, vaporized, erased from existence. Instead, James Webb just watched it breathe. The telescope caught infrared light streaming from the planet's own atmosphere during an 8-minute window, a signal that wasn't supposed to be there, carrying a temperature reading that breaks the entire story wide open. And buried in that single number is the answer to a question our own solar system is going to face 5 billion years from now. What happens to Jupiter when the sun dies? To understand why this discovery matters, you need to picture the life cycle of a star like our sun. Stars don't burn forever. They're powered by nuclear fusion in their cores, where hydrogen atoms slam together under immense pressure and heat, fusing into helium and releasing the energy that makes stars shine. Eventually, that hydrogen fuel runs out. When it does, the star's core contracts while its outer layers expand outward in a dramatic transformation. It swells into what astronomers call a red giant, a bloated shell of its former self, sometimes growing large enough to engulf the inner planets that once orbited safely. Our sun will do this in roughly 5 billion years. When it does, Mercury will almost certainly be consumed, Venus likely too. Earth's fate remains uncertain, balanced on the edge of annihilation depending on exactly how far the sun's outer envelope extends. But the outer planets, Jupiter, Saturn, Uranus, Neptune, orbit far enough out that they should, in theory, survive the initial expansion. The question nobody has been able to answer with observational data until now is, what happens to them afterward? After the red giant phase, a sun-like star sheds those outer layers and pulses, ejecting shells of gas into space and leaving behind only its core. That core becomes a white dwarf, a compact stellar remnant roughly the size of Earth, but extraordinarily dense, made primarily of carbon and oxygen crushed together, glowing from leftover heat but no longer fusing anything. White dwarfs cool slowly over billions of years, fading from white-hot to yellow to red to eventually going dark, though that final stage takes longer than the current age of the universe. The white dwarf in this story, cataloged as WD1856 plus 534, went through exactly that process. Billions of years ago, it was a normal star, probably similar to our sun in mass and temperature. It exhausted its fuel, became a red giant, cast off its outer layers, and settled into the quiet, compact configuration it holds today. It glows with a warm orange hue, radiating residual heat, dim and small and stable. Orbiting that stellar remnant is a world designated WD1856b. It was first detected in 2020 using data from NASA's Transiting Exoplanet Survey satellite, known as TESS, and confirmed with observations from the now retired Spitzer Space Telescope. The discovery team quickly realized something was profoundly strange. This planet, roughly Jupiter-sized, sits less than 2 million miles from its host star and completes a full orbit in about 34 hours. To put that in perspective, Mercury, the closest planet to our sun, orbits at a distance of roughly 36 million miles and takes 88 Earth days to complete one lap. WD1856b's orbit is not just close. It's absurdly, impossibly close for a planet orbiting a star that used to be a red giant. Here's the contradiction that stopped astronomers cold. If this gas giant had always been sitting in that tight orbit, it would have been obliterated when the star was in its red giant phase. The star's outer envelope would have engulfed it completely, dragging it inward through friction with the star's own diffuse outer atmosphere until the planet spiraled into the core and was destroyed. And yet there it was, confirmed and real, circling a dead star in an orbit it shouldn't have survived. For years after that initial discovery, the central mystery remained unsolved. Scientists could see the planet was there, they could measure its orbit, but they couldn't explain how it had ended up in such an apparently fatal location. The leading hypothesis was migration. Perhaps the planet had originally formed much farther out, in a safe orbit well beyond the reach of the red giant's expansion, and only moved inward later, after the star had already shed its outer layers and shrunk down into a white dwarf. That would neatly explain the planet's survival, but proving migration had actually occurred required more than guesswork. It required hard evidence. That's exactly what James Webb delivered, according to findings published in the journal Nature. Using the telescope's sensitive infrared instruments, an international research team led by Ryan McDonald from the University of St. Andrews conducted a series of painstaking observations timed to catch the planet during transits, the brief periods when it passes directly in front of its star from our vantage point. Because both the planet and the white dwarf are small, and because the orbit is so rapid, those transit windows last only about 8 minutes before the planet moves out of alignment. Miss the window, and you wait another 34 hours for the next opportunity. Webb didn't miss. Over multiple orbits, the telescope captured precise measurements during those fleeting transits, and the data revealed something unexpected. When the planet crossed in front of the star, it blocked visible light as expected. But infrared light, particularly in certain wavelengths, was blocked slightly less. That discrepancy turned out to be infrared radiation coming from the planet itself, its own internal warmth glowing outward into space. The team calculated the planet's temperature from that infrared signal and arrived at a figure around 260 degrees Fahrenheit, roughly 126 degrees Celsius. At first glance, that might not sound extraordinary, but when you compare it to the amount of energy the planet should be receiving from its dim white dwarf host, the number doesn't add up. A planet sitting in that orbit for billions of years, heated only by the feeble light from a cooling stellar remnant, should have reached thermal equilibrium long ago. It should be much colder. The fact that WD-1856b is running warmer than its surroundings predict means something added energy to this world relatively recently, at least on astronomical timescales. And the most plausible explanation, according to the research team, is that the planet migrated inward from a more distant orbit not that long ago. The excess heat is residual warmth, the fading signature of that migration event. Here's why that makes sense. When a planet gets pulled into a tighter orbit, gravitational forces from the star begin to flex and deform the planet's interior as it moves through its orbit, especially if that orbit is slightly elliptical rather than perfectly circular. That internal flexing generates heat, the same way bending a paperclip back and forth rapidly makes the metal warm to the touch. This process, called tidal heating, can pump significant amounts of energy into a planet during and immediately after an orbital migration. Over time, as the orbit circularizes and stabilizes, that heat gradually radiates away. But the process takes millions of years. The temperature Webb measured fits precisely with a planet that migrated inward relatively recently and is still cooling down from the event. That single measurement, pulled from 8-minute windows of infrared light, effectively solved a mystery that had lingered since 2020. WD-1856b didn't survive the red giant phase by luck. It survived because it wasn't there when the danger occurred. The scale of what happened here is difficult to internalize. We're talking about an object with several times the mass of Jupiter, a gas giant massive enough to hold over 1,000 Earths inside it, being nudged across billions of miles of empty space, spiraling inward toward a dead star until it settled into an orbit so tight that a single year on that world lasts less than a day and a half on ours. And we're watching the aftermath of that journey in the form of residual heat still leaking out into space. Imagine trying to move a mountain, not by pushing it directly, but by subtly altering the ground beneath it over centuries until the entire landscape has shifted and the mountain now sits in a valley it was never in before. That's the kind of slow, inexorable, gravity-driven process we're dealing with, except the mountain is a gas giant, and the valley is an orbit 25 times closer to its star than Mercury is to the Sun. Now, layer on top of that the fact that we're observing this from 80 light-years away. The light Webb captured left that system during the mid-1940s, while World War II was still being fought on Earth. It traveled for 8 decades through the vacuum of space, and when it finally reached the telescope's mirror, astronomers were able to decode from that ancient light not just that a planet exists, but how hot it is, how fast it's moving, and what its atmosphere is made of. And here's the part that breaks intuition entirely. The planet is larger than the star. WD-1856b has a diameter roughly 7 times greater than the white dwarf it orbits. Picture Jupiter, the largest planet in our solar system. Now imagine it circling something the size of Earth. The visual geometry is almost inverted from what we consider normal. The planet isn't a tiny dot against a vast star. It's a massive globe sweeping across the face of a small, dense, glowing ember. During those 8-minute transits, the planet doesn't just barely nick the edge of the star's disk. It passes across it like a giant curtain being drawn, blocking a substantial fraction of the star's total light. That's actually what makes the observation possible in the first place. The larger the fraction of starlight blocked, the stronger the signal astronomers can pull from the event. But it also means we're looking at a planetary system whose proportions would seem completely alien and backwards if you were standing on a nearby vantage point watching it unfold. The other intuition-breaking detail is time. The planet's year is 34 hours. If you stood on the surface of this gas giant, assuming it had a solid surface to stand on, which it doesn't, you would watch its dim orange star rise and set every 17 hours. Seasons, if such a planet had them, would cycle faster than a single day on Earth. Any moon orbiting WD-1856b would need to circle the planet in mere hours to avoid being stripped away by tidal forces. The entire system operates on a timescale that feels almost frantic compared to the slow, stately orbits we're used to in our own solar system. So, how does a planet actually migrate across billions of miles of space without being flung out of the system entirely or crashing into its star? The answer lies in gravitational interactions, specifically the subtle but powerful way that planets, if there are multiple of them in a system, can nudge each other's orbits over time. Planetary systems aren't static. When you have two or more massive planets orbiting the same star, their gravitational fields interact. Depending on the geometry of their orbits, those interactions can either stabilize the system or destabilize it. In some configurations, planets can exchange angular momentum, the property that governs how fast and how far out they orbit. One planet gives up some of its angular momentum and spirals inward. The other planet gains angular momentum and moves outward. Both orbits change, sometimes gradually, sometimes suddenly. This process is sometimes referred to as planet-planet scattering, and it's been proposed as an explanation for a whole class of exoplanets known as hot Jupiters, gas giants that orbit extremely close to their host stars with orbital periods of just a few days. Astronomers used to think gas giants could only form far from their stars, out where temperatures are cold enough for ice and gas to accumulate. The discovery of hot Jupiters orbiting sun-like stars proved that planets can and do migrate, sometimes across vast distances after they've already formed. WD-1856b appears to be an extreme example of that same process playing out around a star that had already died. Researchers working on the system have suggested that gravitational interactions with one or more additional planets, possibly still lurking farther out in the WD-1856 system, likely triggered the inward migration. Perhaps two planets had a close encounter, flinging one outward, maybe even ejecting it from the system entirely, while sending WD-1856b spiraling inward toward the white dwarf. Once the inward migration began, tidal forces between the planet and the star would have continued to shape the orbit. If the orbit was initially elliptical, tidal interactions over time would gradually circularize it, converting orbital energy into heat inside the planet. That heat is what Webb detected. It's the smoking gun, the evidence that this migration happened not billions of years ago, but relatively recently, possibly within the last few 100 million years, maybe even more recently than that. Understanding this mechanism matters because it tells us something profound about planetary systems in general. They're not frozen in place after formation. Planets can move, they can migrate inward or outward, they can be ejected entirely, they can collide, merge, or be torn apart. And all of this can happen long after the system's formation, triggered by events like the death of the host star, which can gravitationally disturb the entire architecture of the system as it sheds mass and changes the balance of forces holding everything together. The fact that WD-1856b ended up in a stable orbit rather than crashing into the white dwarf or being flung out into interstellar space is itself somewhat fortunate. Migration doesn't always end gently, but in this case, the planet found a new equilibrium, a tight, fast orbit where it will likely remain for billions of years, slowly cooling, slowly fading, circling a star that will itself continue to dim until both the planet and the white dwarf are cold, dark, and silent. But temperature wasn't the only thing Webb pulled from those 8-minute glimpses. The telescope also detected something that had never been confirmed before around any planet orbiting a white dwarf, an actual, measurable atmosphere. And the composition of that atmosphere is where this story takes another sharp turn. As starlight filtered through the very edge of the planet during its transit, that light picked up chemical fingerprints from gases surrounding the world. The data, according to the research team's findings, showed the presence of hydrocarbons, including methane, along with hazes, a kind of organic smog drifting through the upper layers of the atmosphere. The researchers involved in the study noted that this combination of chemistry and haze would likely give the planet a hazy, orange-tinted appearance, not entirely unlike the thick, murky skies seen on Titan, Saturn's largest moon. Finding any atmosphere at all around a planet in this kind of orbit is remarkable. This world has been through a cosmic ordeal. Its star swelled into a red giant, blasted the inner system with radiation and stellar wind, shed its outer layers in violent pulses, and then collapsed. At some point after all of that, the planet migrated inward, potentially driven by chaotic gravitational encounters that could easily have stripped away lighter gases. And yet, the atmosphere is still there, intact, detectable, carrying chemistry that tells a story. That chemistry suggests the atmosphere isn't something the planet acquired recently. It's likely original material, gases the planet held onto since its formation billions of years ago, when it was orbiting peacefully in the outer reaches of the system far from danger. Methane and hydrocarbons are the kinds of molecules you'd expect to find in a gas giant that formed in the cold outer zones of a planetary system, where temperatures allow these compounds to stay stable. The fact that Webb can still read those signatures now after everything this planet has been through implies that WD-1856b's atmosphere survived the entire ordeal largely intact. Some scientists have suggested that this finding could reshape expectations about how resilient planetary atmospheres can be. According to Victoria Bowe, one of the researchers from Cornell University involved in the observations catching these chemical signals required precision timing and sensitivity that earlier telescopes simply couldn't achieve. The atmosphere isn't thick and obvious like Jupiter's. It's a subtle signal, detectable only because Webb's infrared instruments are sensitive enough to pick out small variations in how different wavelengths of light get absorbed as they pass through the top layers of the gas envelope. Here's where the implications start to stretch beyond just this one planet. If a gas giant can hold on to its atmosphere through a stellar death and a subsequent migration into a punishing close orbit, what does that tell us about other planets around other white dwarfs? What does it tell us about the potential for smaller, rockier worlds to survive in habitable zones around these stellar remnants, still wrapped in atmospheres that could, in principle, support conditions we'd recognize as interesting? White dwarfs live for trillions of years, far longer than main sequence stars like our Sun. If a planet can find a stable orbit in the habitable zone of a white dwarf, a region where temperatures allow liquid water to exist, it could theoretically remain habitable for timescales that dwarf the entire history of life on Earth. That's speculative, of course, and no such planet has been found yet. But WD-1856b proves that atmospheres can persist around white dwarf planets. That's a necessary first step if anyone ever wants to seriously search for life in these systems. Not everyone is entirely convinced that the migration story is as straightforward as it appears, and that skepticism is worth examining. While the excess heat strongly suggests recent inward movement, some astronomers have pointed out that alternative explanations can't be entirely ruled out yet. One possibility that's been raised is that the planet could have formed closer to the star than gas giants typically do, or that it migrated inward much earlier in the system's history, long before the star became a red giant, and somehow managed to survive the red giant phase in a different way than models predict. Perhaps the star lost more mass more quickly during its transformation than expected, shrinking its outer envelope before it could fully engulf the planet. Or perhaps the planet's orbit was highly elliptical during the red giant phase, allowing it to dip in close, but spend most of its time farther out, avoiding prolonged exposure to the densest parts of the star's outer layers. These scenarios are considered less likely than the post-death migration hypothesis, primarily because they require fine-tuning several variables in ways that seem improbable. But they haven't been definitively ruled out. Science works by narrowing down possibilities, not by declaring absolute certainty, and in this case, the migration explanation is the one that fits the current data best, but it's not the only conceivable explanation. There's also ongoing debate about exactly when the migration occurred. The residual heat tells us it was relatively recent, but recent in astronomical terms is vague. It could mean 10 million years ago. It could mean 500 million years ago. Pinning down a more precise timeline would require additional observations, possibly measuring how the planet's orbit is still evolving today, or finding other clues in the system that constrain the timing of gravitational disruptions. Another area of uncertainty involves what triggered the migration. The hypothesis that another planet or massive object scattered WD-1856b inward is plausible and fits similar scenarios seen in other exoplanet systems. But so far, no additional planets have been detected in the WD-1856 system. That doesn't mean they aren't there. They could be too small, too far away, or in orbits that don't produce detectable transits from our viewpoint. Or the object that caused the scattering could have been ejected from the system entirely, leaving WD-1856b as the only remaining large planet. Without direct detection of other bodies in the system, the scattering hypothesis remains an informed inference rather than a confirmed mechanism. Some researchers have also questioned whether the atmospheric detection is as clear-cut as it appears. Extracting chemical signatures from such a brief, faint signal is extraordinarily difficult, and the process involves subtracting the star's own light from the combined signal and isolating what's left over as belonging to the planet. Small errors in calibration or unexpected variability in the white dwarf itself could, in principle, introduce artifacts that might be misinterpreted as atmospheric features. The team behind the study has defended their methodology and noted that multiple independent observations across different transits produced consistent results, which strengthens confidence. But this is the first time anyone has attempted this kind of atmospheric measurement around a white dwarf planet, so there isn't a large body of prior work to compare against. That said, skepticism is exactly what makes science robust. The fact that researchers are asking these questions, proposing alternative explanations, and demanding additional evidence is how the process is supposed to work. The migration hypothesis and the atmospheric detection are both strongly supported by the data currently available. If future observations contradict those findings, the interpretation will change. That's not a flaw. That's the method working as intended. Strip away the debates about timing and mechanisms, and here's what we know for certain. WD-1856b exists. It's been confirmed by multiple independent observations using different instruments. It's a gas giant several times more massive than Jupiter. It orbits a white dwarf every 34 hours at a distance that would have been inside the star's red giant envelope. It has a measurable temperature that's higher than equilibrium models predict for a planet passively heated by a white dwarf. And it has an atmosphere that Webb's instruments detected during transits. Those are facts, not speculation. They're the concrete payoff of years of careful observation, starting with the initial test detection in 2020 and culminating in the detailed Webb observations that allowed researchers to publish their findings in one of the most respected peer-reviewed journals in the world. The existence of this planet alone is significant because it provides the first detailed observational evidence that gas giants can survive the death of their host stars and remain in detectable orbits afterward. Before WD-1856b was found, the survival of outer planets during a star's red giant phase was largely theoretical. Astronomers had models, simulations, educated guesses, but no direct examples to point to. This planet changes that. It's a real-world data point that scientists can use to test and refine their models of stellar evolution and planetary system dynamics. The atmospheric detection is equally concrete. Regardless of debates about exactly how much methane is present or how thick the haze layers are, the fact that Webb successfully measured chemical features in the atmosphere of a planet transiting a white dwarf is a technical achievement that proves this kind of science is now possible. The methodology works. The instruments are sensitive enough. Future observations of other white dwarf planets can build on this foundation, and the temperature measurement is perhaps the most useful single piece of data in the entire study. It's a precise, quantifiable number that directly informs our understanding of the planet's history. You can't fake a temperature reading. The planet is either emitting more infrared radiation than it should, or it isn't. Webb measured that it is. That measurement, combined with models of how planets cool over time, constrains when and how the migration could have occurred. It's the kind of hard, reproducible evidence that turns speculation into science. There's also something valuable in simply knowing that a planet like this can end up in a stable configuration after such a chaotic history. Stability matters. It tells us that planetary systems, even after being violently disrupted, can find new equilibriums. That has implications for understanding the long-term fate of planetary systems throughout the galaxy, including our own. Since the publication of the findings in Nature, the discovery has prompted several follow-up efforts. Observing teams have proposed additional Webb time to study WD-1856b in even greater detail, hoping to refine the atmospheric measurements and potentially detect other molecules that weren't visible in the initial observations. There's particular interest in looking for water vapor, carbon monoxide, and carbon dioxide, all of which could provide additional clues about the planet's formation history and internal chemistry. Other research groups are now searching for similar planets around other white dwarfs. WD-1856b was discovered somewhat serendipitously during a survey designed to find transiting planets around a wide variety of stars. Now that astronomers know what to look for and have proven that detailed atmospheric studies are possible, there's growing interest in conducting targeted surveys of white dwarfs specifically to find more examples. If WD-1856b isn't unique, if there are other gas giants sitting in tight orbits around dead stars, each one could add another piece to the puzzle of how planets survive stellar death. There's also ongoing work to search for additional planets or debris in the WD-1856 system itself. If another massive planet exists farther out, detecting it would provide direct evidence for the scattering hypothesis. If astronomers can find a debris disk or the remnants of other planets that didn't survive, that would tell a different but equally informative story about the violence of the system's past. Beyond WD-1856, this discovery fits into a broader trend in exoplanet science toward characterizing not just whether planets exist, but what they're actually like. Webb has spent a significant portion of its observing time studying exoplanet atmospheres, measuring temperatures, detecting clouds, identifying chemical signatures. Each result adds to a growing catalog of planetary diversity that was completely inaccessible to previous generations of telescopes. We're moving from the era of simply finding planets to the era of understanding them. The techniques used to study WD-1856b, timing transits down to the minute, separating planetary signals from stellar light, extracting chemical fingerprints from faint infrared sources, will likely be refined and applied to dozens of other targets in the coming years. Some of those targets will be gas giants, others will be smaller, rockier worlds. A few might even be planets orbiting in the habitable zones of their stars, places where the presence of certain molecules could hint at biological processes. WD-1856b won't be the last planet of its kind studied in this level of detail. It's the first. That distinction matters because first results often set the template for everything that follows. The challenges the research team faced, the methods they developed to overcome those challenges, the way they framed their findings and acknowledged uncertainties, all of that becomes a reference point for future studies. Looking farther forward, some astronomers have speculated that systems like WD-1856 could eventually become targets for even more ambitious observations, possibly including attempts to directly image the planet rather than studying it only during transits. Direct imaging of exoplanets is extraordinarily difficult and currently limited to very large planets orbiting far from very young, bright stars. But as technology improves, particularly with next-generation space telescopes planned for the 2030s and beyond, it's conceivable that a planet like WD-1856b, large and warm and orbiting a very dim star, could become one of the first planets around a white dwarf to be photographed directly. So here's the answer to the question planted at the very beginning. What happens to Jupiter when the sun dies? We don't know for certain because we won't be around to watch it happen 5 billion years from now. But WD-1856b gives us the most detailed preview we've ever had. A gas giant can survive. It can migrate inward. It can settle into a new orbit around the cooling remnant of its star. And it can keep its atmosphere, its identity, its existence, even after everything around it has been transformed beyond recognition. That's not speculation. That's observation. It's a planet 80 light-years away, larger than its own star, glowing faintly warm from a migration that happened relatively recently in cosmic terms, racing around a dead sun every 34 hours with methane and haze still drifting through its skies. Webb didn't just find an interesting anomaly, it found a survivor. A world that went through a cataclysm and came out the other side intact enough to tell us its story, written in infrared light and residual heat. The broader implications stretch in multiple directions. For planetary science, it's a data point that confirms gas giants can endure stellar death, which reshapes models of long-term planetary system evolution. For the search for habitable worlds, it's proof that atmospheres can persist around white dwarf planets, opening the door to future searches for smaller, rockier worlds in more temperate orbits around these long-lived stellar remnants. And for anyone who's ever wondered what the far future holds for the worlds we share our solar system with, it's a glimpse, faint but real, of how this story might eventually end. 5 billion years is an incomprehensibly long time. Continents will drift and reform, oceans will evaporate, the sun will swell, shed its outer layers, and shrink into a white dwarf roughly the size of Earth. And somewhere out there, if the physics plays out the way it did for WD-1856b, Jupiter might still be orbiting, pulled inward by gravitational chaos, warmed by the memory of that migration, still holding onto its atmosphere, still recognizably itself, circling a dim orange ember that used to be the star that gave our world light. We won't be here to see it, but now at least we know it's possible.